I'd like to talk with you about hyperbolas. Hyperbolas are one of our conic sections. And a hyperbola is the set of all points in a plane, the difference of whose distances from two fixed points is a constant. The two fixed points are called the foci of the hyperbola. And I hope you recall that that definition is very much like the definition of an ellipse, but in an ellipse, it's the sum of the distances to two fixed points that is constant, and for hyperbolas, it's the difference of those distances that is constant. So let me show you what I mean. We'll let these 2 points be our foci. I'll let this be focus 1 and this be focus 2. Now, recall the difference is going to be constant. So let's make the difference, the constant difference, be 10. So if this point right here were 2 units from focus 2 and 12 units from focus 1, the difference would be 10 and it would be on our hyperbola. Let's pull away from focus 1, which means we'd need to pull away from focus 2 as well. And let's go right here. Suppose this distance right here were 4, and this distance right here were 14. So it would also be on our hyperbola because the difference between those distances is 10. How about a point right here? Maybe this distance is 7 and this distance is 17, which would again give us a difference of 10. Find all such points and you'll find that the curve goes in this direction. Similarly, there would be points down here, and our graph would look like this. But notice we would have some points on the left-hand side that would be doing much the same. For example, this point right here, it could be 2 units from focus 1 and 12 units from focus 2, and it too would have a difference between those distances that is 10. And find all such points on the left-hand side, and you will have another branch of the hyperbola looking like this. So each hyperbola will have 2 branches to it, and each focus is inside a branch of the hyperbola. Let's talk about how we get the standard form of the equation of a hyperbola. Let's have the hyperbola centered at the origin, and I'm going to put the foci on the x-axis. And I'm going to put one focus at C0 and the other at negative C0. So we want all the points x, y such that the difference between those 2 distances is a constant. So I'll say this is distance 1 and this is distance 2. So we want distance 1 minus distance 2 to equal some constant. I'm going to call the constant 2a. It makes the algebra turn out very well if we let it be 2a. So now let's find distance 1. Remember, this point over here is negative C0, so we can use our distance formula. So we have the square root of x minus negative c squared plus y minus 0 squared minus. Now we have our distance formula between x, y, and c0. So we have the square root of x minus c squared plus y minus 0 squared equals 2a. And then we have our equation of a hyperbola. This particular form isn't very nice, so we could isolate one radical, square both sides, isolate the radical again, and square both sides. I'm going to skip those details, even though they are kind of fun to do. But ultimately, you would get to here. You would get to x squared over a squared minus y squared over c squared minus a squared equals 1. And we make a substitution for this c squared minus a squared, and we let it equal b squared. So our equation becomes x squared over a squared minus y squared over b squared equals 1. And we have the standard form for the equation of a hyperbola that has the center at the origin with foci on the x-axis at c0 and negative c0. And I want you to notice the relationship between A, B, and C right here. I'm going to rearrange it a little bit. I prefer to think of it this way. C squared equals, I'm going to add a squared to both sides, a squared plus b squared, or in other words, a squared plus b squared equals c squared. So you'll notice how similar this equation is to the equation of our ellipse. The difference is that right here, for an ellipse, you have a plus. For a hyperbola, you have a minus. And over here, with an ellipse, you have a minus, and with a hyperbola, you have a plus. But in any case, when I'm thinking about my hyperbolas and my ellipses, I know that these two signs right here and right here are always opposites of each other. Let's do a little bit more. Let's look at these hyperbolas. Notice these two hyperbolas on the left are of the type that I just developed. Here's the equation, x squared over a squared minus y squared over b squared equals 1. And these hyperbolas each open right and left. Notice that they also have asymptotes. Those will be important for us to find when we're graphing hyperbolas. The branches of a hyperbola always approach asymptotes. Notice the orientation of the hyperbolas on the right have changed. These open up and down. And notice how the equation is different. Instead of the x squared first, it's the y squared that's first. The y squared has a coefficient that's positive. So it's y squared over a squared minus x squared over b squared equals 1. And our orientation is opening up and down. Notice the similarity between these two equations. The a squared is underneath the first term. This is different from ellipses. Remember, when you're looking at standard form for an ellipse, the a squared is always the larger of the two denominators. That is not the case for hyperbolas. The a squared is always the denominator of the first term. The a squared can be larger than b squared. It can be smaller than b squared. And a squared and b squared can actually be equal. Now I'd like to show you this example so you can see where the equation of the asymptotes come from. Let's find the graph for this hyperbola. Let's start by finding the intercepts. If you want to find the x-intercepts, as you know, you set y equal to 0. So we would have x squared over 25 minus y squared, which is 0 over 9, equals 1. That means we're solving x squared over 25 equals 1. Multiply both sides by 25, and we have x squared equals 25. So we have x equals plus or minus 5. Now when we try to find y-intercepts, we would make x 0, so we would have x squared over 25 minus y squared over 9 equals 1. That means we have negative y squared over 9 equals 1. Multiply both sides by negative 9, and you have y squared equals negative 9, or y equals plus or minus 3i. So that means there are no y-intercepts. So if I were going to graph this, I know with certainty that I have an x-intercept here at 5 and a y-intercept here at -5. There are no y-intercepts, so that reminds me that the hyperbola is going to open right or left. But the question is, how wide or how narrow should those branches of the hyperbola be? I need the asymptotes so I can determine where those graphs should be headed. Let's look at the graph of this hyperbola as it can be generated on Desmos. Here it is, and notice you can see those x-intercepts are exactly where we found them to be at 5 and -5. But look at this asymptote right here. That's what we want. And we want this asymptote too. What's the slope of the asymptote? Let's see. I want to look at this point right here, because that's a nice readable point. From the center, I would go up 3, so that's a rise of 3 and a run of 5. Where would the 3 and the 5 come from? Oh, they come from right here. The square root of 9 is this 3, and the square root of 25 is this 5. So we can look at the denominators of our expressions to help us determine what the asymptotes will look like. So I'm going to show you in general how this works. So we're back to this equation, x squared over a squared minus y squared over b squared equals 1. With the equation looking like this, we know the orientation of the hyperbola is going to be opening right and left. So let's draw this. And we found in the previous example that the square root of the denominator, in other words, the a, gives us the vertices for the hyperbola. Notice I use that vocabulary. The vertex of the branch of the hyperbola will be at a and -a. But we want to find the asymptotes, and here's an easy way to find them. Go in the y direction, b units. Notice the b is underneath our y, so we're going to go in the y direction, b units. Now, I don't know if b is bigger or smaller than a. Doesn't matter. I'll just put b right here and -b right here. And we're going to draw what some books call the central box. It's a rectangle that goes through those 4 points. Now, the asymptotes of the hyperbola are the lines that contain the diagonals of that rectangle. So I'm going to draw my diagonal and extend it. Oops, I missed, my rectangle isn't very good, but there is my asymptote. And here is my other one. Extend those diagonals to create the lines. And of course, our asymptotes are drawn with dashed lines. And now I can draw my hyperbola. It would open toward or head toward those asymptotes. Similarly, on the left-hand side, same thing. My branch heads toward that asymptote. And I have my picture. Let's do the same thing with the one on the right. One on the right will be opening up and down. The number underneath the y squared tells us how far to go in the y direction. I'm going to go the square root of a squared, or a units in the y direction, and those will be my vertices. So up to a and down to -a, and it's opening right and left. Again, I don't know how wide or narrow the branches should be, so I'm going to draw my asymptotes. To do that, I'm going to go in the x direction, b units. So I don't know how big b is, but we'll just put b over here and -b over here and draw our central box. Now it'd be nice to put it straight edge down and draw those asymptotes. And our hyperbola will open up and down. And we have it graphed. Now I want to mention a couple of things. We should be able to come up with the equations of these asymptotes. Notice in each case you can easily look at your graph and see what the slope is. Notice this is a rise of B and a run of A. So a slope of B over A or B over negative A. So the equations of the asymptotes for the one on the left would be y equals plus or minus B over A x. For the asymptotes on the hyperbola on the right, notice we can look at our picture and see the rise is A and the run is B. So it's A over B or A over negative B. So the equations of the asymptotes for this one would be y equals plus or minus A over B x. I don't memorize whether it's B over A or A over B. I look at my picture and you can figure it out. So again, those are the equations of the asymptotes. One more thing I want to put on our graph, and that is our foci. Remember, each focus is inside the branches, and they are C units away from center. So on the left, it could be somewhere over here, C and negative C. On the one on the right, I'd put it up here, C and negative C. And remember the relationship between A's, B's, and C's in a hyperbola is A squared plus B squared equals C squared. One more piece of vocabulary I want to mention before I finish the video is the fact that hyperbolas don't have major and minor axes like we do with ellipses. Instead, we have what we call the transverse axis. That's the axis that contains the vertices and the foci. So for this problem on the left, this axis right here is called the transverse axis. And of course, that means on the right, this is our transverse axis. The axis that goes in the other direction is called the conjugate axis. So here, this is our conjugate axis. You don't hear that as often as the transverse axis, but I just wanted to mention it. So we have the conjugate axis and the transverse axis when we're talking about hyperbolas.